Now, including water vapor pressure in gas calculations. You can collect many gases by allowing them to bubble up through water into a container that is filled with water. Now, unfortunately, though, molecules of water vapor mix with a gas sample, right? So if you're collecting a gas in, in water, right, that bubbling of water, you're going to include part of that, that pressure of the water, right? So to avoid error, the pressure that was contributed by the water vapor must be subtracted when finding the pressure of the gas. So, as an example, consider hydrogen gas, which is often collected over water. So we're going to collect hydrogen gas, but we're going to collect it in water, right? So the bubbling of the water will be our hydrogen gas, right? But part of that pressure will be the actually of the water vapor. So the hydrogen that is collected in a mixture of hydrogen and water vapor, right? So we're going to use now Dalton's Law of partial pressure, where the pressure total, is equal to the pressure of the hydrogen that we want to collect, plus the pressure of the water vapor. So I've got this table here that shows the actual pressure of water vapor at the various temperatures, right? So if we've got the actual entire pressure that we've calculated, right? Let's say we're given this. We need to find this. So what we want to do is we want to look and find out. So let's say the entire pressure is 100 kilopascals. Right? So 100 kilopascals is the total. So the total pressure within our system. But now we're doing it at a temperature of, let's say, 24 degrees Celsius. Right? So at 24 degrees Celsius. And we're trying to find the pressure of the hydrogen gas. But the pressure of the water vapor at 24 degrees Celsius is 2.98 kilopascals. So I want to isolate for the pressure of the hydrogen gas. So what I'm going to do is I'm going to bring this over. And what I have to do is to make sure that I'm subtracting the pressure of the water from my overall total pressure, right? According to Dalton's Law of partial pressure, you add up all the pressures of all the gases together. Okay? So we've got the total, we subtract whatever we know, which is from this table, right? So 100 kilopascals minus 2.98 kilopascals will give me 97.02 kilopascals. I think that's correct. So, that is now the pressure of the hydrogen gas, right? With a hypothetical. We'll see it with one of the first, with the next sample problems that we're actually going to look at. So what we do is we take the overall pressure, subtract it by the pressure of the water vapor at that temperature to find the actual pressure of the actual gas that we're trying to collect. Sample problem. A student reacts magnesium with excess dilute hydrochloric acid to produce hydrogen gas. She uses 0.15 grams of magnesium metal. What volume of dry hydrogen does she collect over water at 28 degrees Celsius and 101.8 kilopascals? So, let's pretty much take a moment and write out what your givens are and try to put together as well a formula, an actual balanced equation for this sample problem. We have temperature, 28 degrees Celsius, pressure, 101.8 kilopascals. We've got the mass of magnesium, which is 0.15 grams. We've got the pressure of water vapor at 28 degrees Celsius, which is 3.78 kilopascals. Right? So, for those who don't, are kind of tuning in at this point, this number was from the chart I gave in the previous slide. Okay. So, we want to ultimately figure out what is the actual formula that we're using. And here's the actual balanced equation. Magnesium plus 2HCl, hydrochloric acid, produces magnesium chloride and hydrogen gas. So, let's look at what we are given. So from the information that we're given, well, 28 degrees Celsius must be converted to 301 Kelvin. Right? We know our R value, 8.314 kilopascals, liters, moles, Kelvin. Right? So that's our ultimately what we're going to need to find. So from the given, we know that 0.15 grams is actually magnesium. And we're trying to find what volume of dry hydrogen does she collect over water. That's what we're trying to find. Right? So we know now the pressure, the total pressure, right? Pressure total is equal to 101.8 kilopascals. Right? We know that the pressure of water is 3.78 kilopascals. So we're going to have to subtract, right? Because we only want the pressure of the hydrogen gas. So this is the overall pressure subtracted by the pressure of just the water vapor. And now the pressure that we need works out to 98.02 kilopascals. Okay? So with this bit of information, we know what the pressure is. All right? So now we want to find out the actual the amount of magnesium. So we've got magnesium. The mass of magnesium, 0.15 grams. We're going to divide that by the molar mass of magnesium to give us the number of moles. 6.17 times 10 to the power of -3 moles. So now, let's look at this question now. We're being asked to find the volume. So now, we've got the moles, right? We've just calculated the number of moles of magnesium. So now, we can go through the chart, or we can look at the fact that it's a 1-to-1 ratio between magnesium and hydrogen gas, which means if the moles that we found for magnesium is 6.17 times 10 to the power of 3 moles, if it's a 1-to-1 ratio, then this mole ratio is equal for both the magnesium and the hydrogen gas. So now we can actually use our gas law, right? PV equals nRT, to actually find our volume. Right? So it's a 1-to-1 ratio between magnesium and hydrogen. So we don't need to worry about any other calculation. So because it is a 1-to-1 ratio, right, we are going to just substitute. So isolate for V. V is equal to nRT over P. Right? Remember our new P value? Our new P value is that because we take the total subtracted by the pressure that was contributed by the water vapor. Remember, that's using Dalton's Law of partial pressure. So our N value, 6.17 times 10 to the power of -3 moles, multiplied by our R value, which is 8.314 kilopascals of liter over moles of Kelvin, multiplied by our temperature, which is 301 Kelvin, divided by our pressure, our new pressure, which is 98.02 kilopascals. So we know volume is going to be in liters, so let's just cancel out here. We've got Kelvin, Kelvin, moles, moles, kilopascals, kilopascals. Last unit standing is volume. So when we do the calculation, we get a volume that is equal to 0.1575 liters. Now, according to the question, least number of significant digits is 2, so we want the 0.15. We look at the 7, and the volume of the dry hydrogen that's collected is 0.16 liters.